the Habitable Worlds Observatory. This is going to be a next generation space telescope that should give us the holy grail of exoplanetary astronomy. It should give us the first direct images of an Earth-sized world orbiting around a sun-like star. It should be able to detect the atmosphere of that world and give us valuable clues about whether or not it's even inhabitable. But this telescope is a long ways off. There is a lot of technology that needs to be developed, risks that need to be analyzed, new rockets that need to be considered, and a lot of work that needs to go to every phase of this project. From the shape of the mirror to the design of the coronagraph that'll block the light from the star to be able to reveal the fainter exoplanets beside it, to the level of serviceability. Can we upgrade and update this over time when it's out at the L2 Lagrange point? There's a lot of questions, and yet there's a lot of science that is waiting on this. This is the top priority for the exoplanetary community, and they have made their interest very clear at the most recent decadal survey. And so my guest today is Dr. Lee Feinberg. He was the principal architect for the Habitable Worlds Observatory. He was one of the people behind the James Webb Space Telescope, and he is going to be the mission architect for the Large Interferometer for Exoplanets, which is the other mission that is going to be potentially finding Earth-sized worlds orbiting around sun-like stars. He is a legendary telescope spacecraft designer and knows more about space telescopes, mirrors, optics, all of the bits and pieces that come together to make these next generation space telescopes. And we got a chance to talk again, which is amazing. He's one of my favorite people to interview because he is so knowledgeable and is able to also explain it in a way that makes it very accessible to anyone who's listening. And so if you've got questions both about how James Webb is doing right now, how is the health of the telescope, how has it matched the expectations of the astronomers, this is the interview for you. If you're excited about the Habitable Worlds Observatory, you want to know when this thing's going to get built, what kinds of technologies are going to go into it, what should it be capable of accomplishing, this is going to be the interview for you. But we've also got information about the Large Interferometer for Exoplanets, which is the European version of this. Totally different technology, and yet should give us the same result. We also talk about quantum telescopes and a lot of other random stuff about interferometers and telescope ideas. Like if you watch one interview on my channel this year, this is going to be the one. All right, without further ado, enjoy this conversation with Dr. Lee Feinberg. Lee, it's good to see you again. And first, congratulations on your retirement.
Thank you. It's only been 5 days, so I'm still kind of getting used to it, but yeah, it's only a 2-month retirement.
Yeah.
So
well, that's the part that I was just about to go into. Congratulations on your new job.
Yeah, my new job. Right.
Yeah. All right. Well, we're going to get into all of that, but so just to sort of let people know, we're going to be talking about how James Webb is doing, the design work that Lee has done on the Habitable Worlds Observatory, his new job, which is going to be working with the LIFE mission out of Europe, the Large Interferometer for Exoplanets. So, and then an update on quantum telescopes. We've got a lot to talk about. So first, let's start and talk about the health of Webb. How is the telescope doing?
It's doing amazing well. To be honest with you, every time I talk to you, I tell you it's doing amazingly well, and it's still doing amazingly well. Start with the optics, right? I mean, you see the images coming out of it. There's been almost no degradation. We've gotten a few more decent sized micrometeoroid hits, not as big as the one we got that first year, maybe like a third, but we're not even seeing it in the, you can barely notice it in the data, and the projections look great, on the optics. So.
And that was like, after you got that big ding in one of the mirrors, you reoriented the telescope, changed kind of the way you do the observing. And does it feel like that worked?
Yeah. So we have this thing called micrometeoroid avoidance zone where we try and point away from the ram direction whenever we can. A few times you still have to because of certain, objects in the sky that are only available at certain times a year. But we predicted it would reduce, the number of these sort of big hits by about 30%. And we're seeing exactly that kind of reduction. So it's doing what it was intended to do. But it's not, and over decades, it'll matter. But it's not making them zero either. But we're fortunate they're just small. We're just not getting big impacts from them in terms of the effects on the optics. It's consistent with what we've seen and we've been up for over 4 years now. So
well, that's the thing. Like we are almost halfway through the provisional mission. Well, at this point,
actually, the requirement was 5 years. The mission had a 5-year requirement, 10-year goal. So yeah, I mean, a year from, and we really judge it based on the beginning of science, which was July of 22. So this July will be 4 years of science. We'll have 1 more year of science to officially meet the level 1 requirements. And we're on track. It's on track to do that. And there's really fuel was one of the issues early on. Remember, we worried about fuel. I mean, the fuel projections are crazy. We've been quoting over 20 years for a while. And I think the numbers are much even better than that by quite a bit.
Really?
Yeah.
Oh, wow. Okay.
Yeah. And they've been using less fuel for station keeping and all that kind of stuff. So fuel looks great. I think in the end, whether this thing lasts for, many, many decades might be more dependent on other subsystems, typically things like, power and communications and basic electronics that can degrade in certain scenarios. Hubble saw some of that. Power is somewhat subject, solar rays get hit by micrometeoroids and things like that. And there's solder joints in the system. So, I don't think we can say for sure that this is going to last many, many decades, but it's certainly possible. And my bet is it'll last longer than people ever had dreamed, so.
Yeah. I mean, for me, I always am most nervous about the reaction wheels and the gyros.
Yeah. So let's see, Hubble, the wheels were a big deal and we had to replace them, because they had mechanical bearings, but the wheels and gyros have gotten better over time. I mean, now we're using things that just don't wear, we have technologies that don't wear. So, I don't think either of those are a particularly big concern. I mean, the wheels I would keep, you still do have some wear on over time with bearings and stuff, but gyros not so much anymore because the types of gyros we use. And even on the wheels, there's no real degradations that have been a concern. There's some degradation in some, like the mid-infrared channel of MIRI, there was some early degradation at the very longest wavelengths, where maybe it's radiation related, et cetera. So there's been some slight degradations in a couple of the instruments, but some of those have even tailed off. But for the most part, I personally, and I've been spending way less time on Webb personally this last year because things have been working so well. But I haven't heard of anything that has made me think that it won't be well over 10, 15 years. And I think, maybe I expect things like power and comm and that kind of stuff to be the biggest concern areas in the future. Yeah.
Right. And that, if we really are decades into the future, then hopefully that's more time for better spacecraft to come along to help maybe do servicing missions. Like things that seemed like science fiction now start to go, maybe we could send a Starship up there to repair
100%. In fact, I've been a big advocate of servicing HWO, either with something like Starship or a separate servicer and a robot arm. And one of the arguments I've been making to people is if we can service HWO, you could also service Webb someday. I mean, it was a large investment in money, and if a relatively simple servicing mission could extend its life, it would certainly be worth considering, in the future. So yeah, I agree with you. I think robotics and autonomy are going to be so enabling in the future, especially at L2, where you have this something like 6-second delay. So you kind of need some level of autonomy anyway. But even without, advanced autonomy, we could do it with current state of the art. In my opinion, it would be more a cost issue. But I think what's going to happen in the future is it's going to be less and less expensive because the infrastructure is being developed. There's probably going to be these, robots floating around in space that can do stuff and that can kind of think on the fly. So, yeah, I think there's a good chance we could extend its life with some sort of servicing if it's needed and if it makes sense. I mean, it depends on what the issue was, right? But yeah.
Yep. And then just like, what about the science? I mean, there was all the expectations for the quality, the resolution, what you were going to be, what you guys were going to be able to deliver to the scientists. And I mean, obviously they're going to say this sucks, we don't like it. But, are you finding that they're able to be as productive with this data as they were hoping?
The best moments, Mike Menzel, the mission system engineer, and myself, it's like, we love going to the American Astronomical Society meetings because there's nothing like having like all these scientists working with Webb, thanking you for. And I'll tell you, the last one, it was like a lot of the members of the science working group in particular were really, walking up saying it's amazing how well it's working. And, they all do different science in every one of those areas. They're doing better. The image quality is better than we expected. And because of that, the spectroscopy has higher efficiency. You're putting energy through a slit and you have better image quality. It means that you're getting more energy through. So you're getting better throughput on your spectroscopy. You're getting, the stability is insane. We're killing it on stability. So like transit measurements, early on, we had this thing called tilt events that occasionally a mirror would kind of suddenly move. I don't know if we talked about that, but it was something we tracked. We saw it in the test program on the ground, and we thought over time there was some like frozen in strain that would relieve itself. But you always worry a little bit until you actually see it. Like, and we saw literally the very first transit we did. We saw a couple tilt events. We could actually see in the wavefront data that the mirror tilt all of a sudden kind of jerk, like something was holding it. There's a little stiction and the strain in it pushed, a little jerky motion. But they're almost gone now. So over time, these things have kind of, the strain's relieved itself, which, if you think about it, it's a 50 Kelvin telescope. You launch it at room temperature. So as it cools down, you're freezing in a lot of strain in the actuators. You got the backlash, you got joints and all that. There's a little, motions early on. That's all gone. So things are more stable than they've ever been. We've seen some small changes in temperature, but you expect that. Thermal insulation degrades very slowly. Nothing surprising. We never had any ice problems. That was something we worried a lot about. All these cold temperatures, and if you get, water that's from somewhere warm, like electronics, that comes and hits a mirror surface, not getting any of that. So yeah, the scientists are they're doing everything. As the early universe science is killing it. They're finding things, little red dots that they're different explanations for. The transit science, the exoplanet science. I mean, they've come up with new ways to do things that were never even originally envisioned. Really clever strategies for chopping from one TRAPPIST planet to another, or looking at day-night transit. I mean, all sorts of great stuff. And I will say, having the full suite of instruments, MIRI and near, the near infrared, has been really great because they each have their own strengths, right? So yeah, they're killing it everywhere. I think the scientists are super happy.
Yeah, that's great.
Yeah.
All right, so everyone can breathe a sigh of relief. Everything's going great with Webb, and it looks like it's going to have even longer out there than anyone had possibly hoped. So this is all terrific news. So then let's shift gears now to the thing that everybody is really excited about and won't stop asking me. And so now I'm just going to go right to you, which is, let us know sort of what is the status of Habitable Worlds Observatory. You have gone through a design phase at this point. Where did you get to?
Yeah. It's kind of interesting because when I was retiring, I was talking to Dave Redding. I don't know if you knew Dave from JPL. He and I worked on some of the very earliest concepts for at least a segmented version of this mission. And he pointed out to me, we started working on it 18 years ago, 2008, for the 2010 decadal.
Right.
So that's how long these sort of ideas have been bubbling around. But the last, I'd say, 2 to 3 years have been really we've really increased the amount of progress significantly. And, we're still not getting, hopefully very soon, there'll be real funding, the kind of funding that was envisioned by the decadal. But even with, but we've been getting more funding than we ever got. So we actually have a full integrated modeling team that has been looking at architectures. And there was a conference in July in Washington, D.C. That was extremely successful. It's all on YouTube. It's really, 3 days, 4 days of talks, really, really outstanding summary of everything. And then there was a bunch of papers that have been coming out. There's a science summary, but then also all the papers that are going into a special issue of JWST, including a paper I did that's now on archive, that kind of summarizes, we started with 3 different architectures. We called these, we came up with a name, exploratory analytic concepts. And, the way I describe it to people is I say, if you're building a rocket, you can afford to build multiple rockets, and then the first one doesn't work, you find out why, and then you iterate, and that's sort of the way Apollo was developed and Starship is being developed. Well, with space telescopes, you don't quite have the luxury of building multiple space telescopes. So we build integrated models, and we look at, things like mass and volume, but we also, and architectures, right? Architectures that you then model, and you say, how much mass does this thing have? How much volume is it taking up? But also performance, looking at the performance. So we did the first 3. One was on axis, 2 were off axis. One was 8 meter. The other 2 were closer to 6 meter. And we probed different aspects of parameter space. And then last spring, we down selected to 2 architectures that are now called EAC 4 and 5. And my paper I did summarizes kind of that whole effort from the first 3 to the next 2. One of the things we did, though, is with the EAC 1, the very first one, we went really deep on the integrated modeling and, really pushed active controls. To get to picometer level, you need layers of active controls. You need active controls on the heaters and the mirrors. You need some sort of metrology between the segments. And then you need, sort of active line of sight motion. You have all these different loops working at different. So you got to put all that together with control algorithms. So when we do modeling, we're trying to get all the way through all that and actually get to the point that we can look at, science from the point of view of, Earth-like planets at different distances away from a star, different inner and outer working angles, what the contrast is, what the dark zone looks like. And the modeling now, I will tell you, I was at a meeting actually last week, right before my retirement, literally that day. And we were reporting, they had the industry teams that are been working and are getting funded in the next generation of technology efforts. And the results are showing that we're now getting modeling that's at the almost single digit picometer wavefront performance, which gets us to the,
Yeah, I was going to say, give us a sense then with picometer wavefront performance, what kinds of targets does that make available?
Yeah. So, we're going after these Earth-like planets around sun-like stars. So that's number one, sort of FGK stars. The couple big challenges. One is you need very high throughput, so the chronograph has to be designed for that. We want to get really good, what we call inner working angle, which is how close to the star can you work. And the reason is, the way I think of it is, here we are in our solar system looking out at these other solar systems. If we can get closer to the star, then that uncovers more stars. Think of a sphere that's growing. And if I want to get a star that's even farther away, the planet will look closer to the star just because of the angular extent. So if you can get closer to the star, better inner working angle, you uncover more stars. And the whole idea is to uncover enough stars that we get at least 25 exoearths. But really would like to have even more than that, to have some margin, right? And to do that, depending on what they call edus of Earth, how frequent are these Earths and these systems, but you're probably looking at surveying a good 300 to 500 stars. And the closer to the star, the bigger the aperture, the better the inner working angle. So EAC 5 is the big one. It's 8.2 meters inner diameter, the inscribed diameter. And it's like 10 meters on the, outer diameter.
Huh.
That's
so I thought that they had sort of decided they were going to go with 6.5, the same size as Webb, but that's still open to go bigger.
Yeah, the EAC 4 is 6.5 meter inner diameter. So we're trading, which by the way is still bigger than Webb, because Webb is 6.5 meters outer diameter. So we're trading something that's inner diameter is about 6.5 meters. That's the EAC 4 with something that's closer to 8 meters. And they're both off axis. We decided to go off axis. That's a big. Now the question is, why did we go off axis? Why did we not?
Yeah, I mean, even can you describe to people what off axis is, and then what are the benefits of that?
Yeah. So it turns out that, so on an on-axis telescope, which Hubble and Roman both are, the secondary mirror is right in front of that primary mirror. It obscures it. You can think of it like blocking the center of it. And because there's an obscuration, because it blocks part of the light coming in from the star, you're losing maybe 20% of the throughput, depending on the size of that secondary. But there's a couple other key factors that when you're trying to looking for Earths with a chronograph, a high contrast chronograph, that secondary mirror, create. And one is one of the leading coronagraphs that we really like types is called a vortex coronagraph. A vortex chronograph is a chronograph that kind of rotates the polarization in a way that creates a really good dark zone. It's complicated, probably a little complicated to get into all the details of it, although I'm happy to if you want to. But if we want to use a vortex chronograph and get the benefits, one of the key benefits, there's two key benefits in my mind of it, or maybe three. But one is it gets better inner working angle, which we want. But the second is it's very insensitive to stability of the primary mirror, especially in the sort of low order modes, which are important modes that are difficult. So anything we can do to make the stability problem harder, get better inner working angle with very high throughput, we would want, which is vortex. And the vortex technology isn't quite there yet. It's more at the 10 and the 9th level, and we need to be at 10 of the 10. So that's one of the key investment areas. But if they get there, it really benefits from having an off-axis system, a system that's not obscured.
Right. And so the light's coming in, it's bouncing at an angle off of the secondary
mirror,
off the primary mirror, and then the secondary mirror is outside of is no longer in the way. Yes. And then bounce the information to the instruments, and you've got, and so that's the equivalent of you making a bigger mirror. That if you had Hubble or Webb or Roman if they were off axis, then they wouldn't be losing that 20%.
Yeah. And a really important point is there's this thing called diffraction, right? Which is it's a wave effect, a physical optics wave effect. If you have a secondary mirror sitting there, at the edge of that mirror, you get diffraction, which creates these little waves. And that's one of the things that makes this using a vortex challenging, is the diffraction from that secondary. It really makes all coronagraphy a little more difficult if you have an obscured system. And it's the reason why, if you're really trying to push contrast, these 10 to the 10th, by the way, is really hard. That is, we've gotten one, or they've got maybe like 2 or 3 times 10 to the minus 10, but we need to do it over a reasonably good, we call it bandpass, over a fairly large amount of wavelength. Because otherwise, if it was just a tiny little sliver of wavelength and you had to rotate, it would take forever, or move it. So we need a decent amount of wavelength range, a bandpass, while we do all this. And so there's all these different trades. But it turned out that diffraction effect, the effects on the vortex chronograph of the on-axis were painful. The belief was that the on-axis would be simpler because the secondary mirror is actually closer to the primary, almost by a factor of 2, which is a big deal. And that there's reasons because of polarization where you can't just put the secondary mirror any closer with an off-axis telescope. But here is I think the thing that was most surprising, and the integrated modeling showed this, is that, okay, well, how do I stabilize that secondary mirror if it's on axis? I need struts to hold the secondary mirror. You've seen the struts in Hubble and in Roman. Roman has 6 struts. A lot of telescopes have 3 struts, the famous 3-strut diffraction pattern you see on Hubble. But if you're a chronograph, you want those struts to be really thin, because otherwise they create a lot of diffraction. So we needed really thin struts for that on-axis to hold the secondary. And it turns out it's really hard to make a stable telescope, to hold that secondary in a stable way with really thin struts. And that was something we could only figure out from integrated modeling. And it was not completely intuitive to me. I thought we would be able to achieve a more stable secondary. And in fact, what the team came up with was, well, maybe what we'll do is we'll run a tower up the side where you have all the beauty of the off-axis, by the way, is you can have a tower holding that secondary mirror, and you have all this volume that you can use for the tower. So I call it the Eiffel Tower. You can build an Eiffel Tower to hold the secondary mirror. Well, even for the on-axis, we were finding ourselves building a bit of an Eiffel Tower on the side, but then you still had to come across and hold this thing in a stable way without big struts. So I think that was one of the most surprising things we learned from the integrated modeling, and it led us down more towards going off axis.
Yeah, and the images that have been shared by NASA to us, we're still regularly showing the three designs with, kind of, they all sort of have different shrouds. But the thing that I guess you're driving at is that you can have this, as you call it, an Eiffel Tower. You can have the secondary construction sitting off to the side, yes, one component that's very strong, can be as beefy as it needs to be, and that you're just then angling your mirrors to push that light off to the side. And so really the question is, can you get that light angled in the right direction and control it? But then you don't have to really worry about both making a beefy enough secondary mirror assembly as well as it not getting in the way. So it sounds like it's a very elegant, like, do you feel in doing this, you're like, okay, all future space telescopes are going to be off axis?
I don't know if all are. I was interested that this Lazuli telescope that Schmidt is funding went off axis, and they're putting a vortex in their coronagraph. So, they're going to kind of be a little technology demonstrator for some of the ideas that we're talking about. They won't be nearly as stable, but still they'll be able to learn something from that. So I think for people who want to really push coronography, this is probably something people will want to do. It's not something you typically, at 10 to the 6, Hubble had a, STIS, which I worked on. There's a little chronographic, thing that sticks up, and it's like 10 to the 5th, 10 to the 6th. When you're at 10 to the 10th, you kind of need to worry about every little detail like this. But let me just tell you one other really critical point. This is why it was such a complicated thing, and it's still, got to nail down. But they still have to select between these two architectures. But the other part of all this is what rockets will be available when we launch this. And what we tried to do, and this is a really key point, is we tried to make it compatible with Starship and where it's going. And we're using the current version of Starship, even though there's been some bigger versions and sketches. We've been meeting with all the different companies, including SpaceX and Blue Origin, and we're sticking with the current Starship. Blue Origin has this next generation rocket that they announced last, I think, summer timeframe. We were already in conversations with them about that, and that one is actually a bigger volume. Its volume is very similar to Starship, not as much mass, and it's a little bit longer than Starship, but not as much mass.
Right.
And so
the Starship one is what? It's a 9x18 fairing, right? 9 meters wide, and it's an 18 meter tall fairing.
Yeah. The 9 meters part is right. The height is a little misleading because it's not just the height at the peak, but it's that shape, the cone shape.
Right.
If you look at the pictures of what we're developing, you have to fit in that cone. So for Starship, we're like a little tight on it. For the big one, the EAC5, on Starship, we're a little tight on volume, and with Blue Origin's next generation, we're tight on mass. And so I think this is now me no longer working in NASA telling you what my opinion is, but I think where EAC6 will wind up, which is the one that will actually do, is it'll actually be a little bit smaller than EAC5 in order to be dual compatible with both Starship and Blue Origin, both in mass and volume. But it'll be probably closer in size to EAC5 than EAC4. I mean, it'll be in between. The one difference between EAC4 and 5, though, is EAC4, the primary mirror, although segmented, it doesn't have wings that unfold, whereas EAC5 does. So it has wings. So that's one big thing that the team needs to decide is, are we going to have wings or not? And when you have wings, think of the Webb wings, the two mirrors, you also need the barrel to go around the wings. And so it complicates the barrel. So wings complicate the barrel, but they allow you to fold the thing up when you ship it. And the logistics of moving this thing around get a lot easier. If you look at Webb, we put it on a C5C to move it around the country. And that was enabled in part because it folded up. And especially, at a minimum, you're going to have to fold the secondary mirror up. But my guess is the team's going to conclude they're going to want the wings for that element. And then it's just a question of how big can we go to have enough mass and volume margin. This is just my reading of where we are, and kind of, talking with the team about what the next year and a half will look like. Yeah.
But from a kind of a simplicity perspective, ideally, you'd want to go the I don't know, like the Herschel route or the Nancy Grace Roman route, where it's just a tube that sits inside your fairing.
And that's what
and
EAC4 basically, there's two different concepts for EAC4, but one of them is at least a half a tube and part of the barrel deploys. And then the other one has the primary mirror, instead of kind of face up like Roman, it's face sideways, but it doesn't need to deploy, but the barrel's kind of ready to go. So EAC4 would definitely be less expensive and would be simpler, but we talked earlier about inner working angle, right? And you just don't get the same inner working angle, and you don't get the same collecting area, which is critical for spectroscopy. And this whole search for life thing is all about signal noise.
Yeah.
So
right, but it is always the balance. I know that if they get to the final design and it's got a whole bunch of moving parts in the same way that James Webb did, like a lot of people are going to go, I don't want to go through that again, right? And I think that was, like a lot of that added time, budget, and just concern and anxiety to everybody involved.
This is all and then there's one other really key factor architecturally, which I didn't appreciate till last spring. That's why these early architecture studies have been so valuable. And that is, okay, so you got a coronagraph, and, in an ideal world, this coronagraph would have a visible channel like the coronagraph that's in Roman. It would have a near infrared channel and a near ultraviolet channel. But let's talk about the near infrared channel, because that one's pretty critical, because the vis channel does not get you, for example, methane, and it can't rule out false positives. Okay. So if you really want to rule out false positives, if you want to say whether you have found life, okay, you kind of need the near infrared channel. Now, later, we're going to talk about the life mission and what it could bring to the table. But at least if HWO wants to do it, it needs near infrared. Well, near infrared, because of, just think of resolution as wavelength over diameter. So if you go longer in wavelength, your resolution goes down, which means your inner working angle goes down. And it also turns out there's more zodiacal light at those wavelengths. So like you lose like a couple different ways in the near infrared. And when you start looking at the exposure times in the near infrared, a 6 meter the exposure times are crazy long. And so scientifically, if you want that near infrared, if you want to be able to rule out false positives, you kind of need to be much closer to the 8 meter scientifically. So the scientists, and there's a lot of other science, by the way, the intergalactic media science, as an example, really wants the 8 meter. There's really good arguments. There was a great talk by David Charbonneau at the American Astronomical Society meeting. He's the co-chair of the Community Science and Instrument team for the Habitable Worlds Observatory. He basically stood up there and said, almost every science we're doing wants as close to 8 meters as possible. And and that's what the science, community has realized. And here we are having the exact discussion you're having about the 6 meter versus 8 meter in terms of complexity. And so, it's a cost benefit trade that the team needs to make. And you might argue, yeah, Webb was really complicated and took longer. Well, the one thing we could have done to make Webb simpler, if you look at history, and I know this because I was sort of involved a little bit, but the one thing we could have done was not had a mid infrared channel. Now, can you, no MIRI. Can you imagine Webb without MIRI?
No.
And that's kind of what we would be arguing. Like we go 6 meter, we wouldn't have the near infrared channel. It's almost that drastic a change.
Right. Oh, I want to go back to sort of this idea of using HWO for finding planets versus observing planets. It's kind of, it's so weird to me. We're at this point still, like with the loss of the Kepler mission, we never went through this phase where we were identifying Earth-sized worlds orbiting around sun-like stars that could then do follow-on observations with a telescope like that. And I mean, Plato can maybe do some of this. TESS, if we're really lucky, might find one. The Extremely Large Telescope comes online, but it's more for observing things that we know about. So is there no sort of plan to kind of break this up? Let's build a finder first, and then let's follow on with something that can do the imaging.
There's been arguments about using, for example, radio velocity to help find targets, and some of the folks who advocate star shades have pushed that. I A couple thoughts though. One is, HWO is really built for the blind search problem of surveying hundreds of stars and not looking once, right? Because these planets are going around the star, and then once you find it and you get their orbit, you're talking about going back multiple times. And so that's why, something like a coronagraph is so ideal to look, then to come back in 6 months or whatever it is. So that's a key factor. The other key factor is, even if radio velocity can get some, generally the feedback I've gotten, I'm a systems and I'm an architect, so I'm getting input from scientists, but most people don't think that method will be able to work on every target. That some targets will have too much, the stars themselves will be too active to be able to do it really well. And there's a debate about how well it can do it and all that. And so it is possible that some of the targets could be found, and then you could even potentially use some sort of star shape for those targets. Although again, it's difficult because you want to get multiple readings as it goes around. But I think, if you really look at this, to me, problem one here is surveying hundreds of FG and K stars, and to do it as well as possible. So like the big aperture, ultra stable telescope is the way to really do the survey. Once you find those targets, the best two possible ways to go about studying them are star shades, which maybe fills in things like the near ultraviolet or bandpass, and interferometry in the mid-infrared, particularly for follow-up. Some people would want to search with it as well. But, but I really think HWO's strength is to be able to survey hundreds of stars, go back multiple times, and, really characterize the dynamics of these things, how they change over time. There's a lot of reasons why you want this persistence, if you will. And that's the strength of this approach, providing that the coronagraphy gets there with its sufficient bandpass and throughput and inner working angle,
Yeah. Well, and I mean, Nancy Grace Roman, which launches, now about a year away from that taking off, it's going to have this prototype chronograph on board that's going to get us the exojupiters orbiting around sun-like stars. So, I've interviewed sort of people on that team, as well as the people that are working on the next generation, the kinds of technologies that'll work for HWO, and it'll be interesting to kind of see incrementally to move towards that. So when we think back to James Webb, we think about the technological readiness levels for the various stuff, and there was a bunch of big gotchas, and essentially they had to invent the technology from square one. When you think about the technological readiness level to get the kind of science goals that astronomers want, what feels like it's going to require the most energy and effort to kind of remove the risk?
Yeah. I mean, the big two are getting the contrast with, the throughput and the bandpass that you need. And then getting the stability, right? Those are the two big pieces. I think the first one is a little harder in a sense that the best results in the lab are still a few times 10^-10 and not at the 20% bandpass level. And there's still things that those tests aren't fully mimicking in terms of what the coherence of a star would really look like and the stray light of the systems. So I think, really demonstrating that you can get real close to 1 × 10^-10 with sufficient inner working angle. Now, if the telescope is serviceable, and this is a key aspect of the whole architecture, which I think this is something I actually talked to the administrator of NASA about, was what I really think will enable this mission is making it serviceable like Hubble was. So that maybe you don't need to start with the world's, a perfect chronograph, but you do need to demonstrate that the chronography can get to 10^10. Roman's at about 10^8, and they use post-processing to get to 10^9, but it's very low throughput, about 2% throughput or some real small number like that. We're trying to get to 30-40% throughput with 10^10 to 20% bandpass. So you need to be in the 10^10 regime, or you're simply just not going to find Earth. But you also need a decent throughput and bandpass. So I don't know that the bar that has been set is you probably could go below that, but on contrast, you really can, and you really need enough to convince yourself it's worth doing this mission. That you'll get enough of a survey. I think that is the single hardest, most important thing. I think there's still the possibility. They say when we in the lab there's some incoherent light. that they don't understand. In other words, they use the deformal mirrors. Deformal mirrors are working coherently, right? The light is coherent, like a laser is coherent, and you can conjugate something coherently. You can invert the phase of that thing using a deformable mirror. But if you want to, but there's light that's bouncing around that's incoherent. And it's like, what is that light? Why are we not getting the 1 times 10⁻⁻10? What is the source of that incoherence? And it may be that the temporal coherence of the source. That's one of the possible things. One of my colleagues, or two of my colleagues at Goddard, Dr. Bobak Saif and Dr. Brian Starsky, literally, I love telling the story. It's like when the government was shut down and everybody was taken off, figuring out, working on their basements or whatever, they literally did physics for 10 hours a day, trying to figure out the source of this incoherent light. And they really focused on the coherence is temporal and spatial coherence. And so this is one of the things that they have been thinking that we need to evaluate. And so now we're going to hopefully run some tests over the next few months looking at. But this is something that has to be solved, is what is the source of that incoherent light? And the JPL team, who are of course the leaders of a lot of this technology, they've been chasing this with, here's the possible sources. And in some cases, they're finding stray light to be a source. In other cases, it's the how well you can move the deformal mirror in fine increments. There's, it's one of these death by 1,000 cut things as well, but there may be one or two big hitters that we're looking for. The other big thing is stability, though, is those mirrors are going to have to be stable to the handful of picometer, a few picometer level. We've done it at the single degree of freedom, and we're able to measure picometers now in the lab. The really hard problem, we measure picometers all the time now, single digit picometers, from one patch of a mirror to another. The hard thing is going to be doing this over fairly large mirrors, and doing it for long periods of time, what we call drift. And there's been a lot of progress. There's a new test facility coming online at Goddard called the MiniMust, which is the mini metrology ultra stable test bed. But a lot of the technologies, ultra stable mirrors that L3 Harris is building, the active metrology that folks like BAE are building, and folks like JPL and University of Arizona are going to be contributing to, those are all going to be tested in this facility. So those groups are going to be developing the active controls. And then the other big thing, for vibration, which affects stability, one of the companies being funded is Busek, which makes microthrusters. And the models are showing, if you use microthrusters for stable, for station, staying pointed, right? Like, how do you keep the spacecraft pointed? Use this very small amount of thrust, this micro thrust, and it's continuous. You just don't get the kind of vibration you get using reaction wheels running at high speed. And so what we could potentially do is use the reaction wheels to slew, and then use micro thrusters or some sort of isolation. Lockheed's been working on some isolation technologies as well, that this basically, they're voice coil systems that isolate things. So all of this together, everything I'm talking about, stability and contrast, that is the key.
Right. That all has to come together.
All has to come together. We also need detectors to improve a little bit. But on the detector front, a lot of them are affected by radiation, but that's where servicing can make a big difference. Even if we don't have a perfect detector, we just need a good enough detector to last 3 to 5 years and potentially have a second generation.
So people ask me when will this probably fly, possibly fly, maybe fly, and like there's no official dates. I hear 2030s, 2040s, and obviously we saw timelines slip for James Webb as reality reared its head. What is the sort of the kind of the general target area that the community is hoping to aim for?
Yeah, and the administrator a couple times has sort of said, "Oh, I'm intrigued by HWO, but it's going to launch the 2040s, and I want to see if we can do something sooner." Which was one of the reasons I reached out to him and talked to him about this. Yeah, first of all, the plan is to have the mission concept review in 2029, and these technologies I was just talking about would mature to, they call it TRL 5 level, but close to that anyway, by that time. So in about 3 years, we would have the technology sufficiently mature to really ramp this project up. And that would be the point in time we'd really know the schedule. But the thing I will tell you is, and I've said this, I said this at a meeting with the whole team recently, is like the getting the technology mature on this project is the hard problem. once you do, I think actually building this can be a lot easier than Webb, because Webb, was a cryogenic telescope. So we had to build, figuring out how to test Webb and, how to do everything in cryogenic. Cryogenics took a lot of time to cool things down and warm them up and material properties. So I think actually building it's going to go a lot faster. And we've learned a lot of lessons from Webb about how to architect it and how to do things in parallel and how much they really should cost. I mean, we're not going in with something where we've highly underestimated it. If anything, I think they overestimated it, to be honest with you. Yeah, my belief is they overestimated it. And, if you look at the timeline Roman just took, of 8 to 10 years, I don't think from mission concept review, something like that is not I think something like that is possible.
Right. So 10 years. So end of the 2030s, early 2040s.
I think just, now I don't work for NASA, so I say my opinion, but I if I was there, I'd be pushing for, late 2030s. And I would really push the team to, but rely on servicing so that you simplify. Because see, on Webb, this is a key point. On Webb, we couldn't service Webb, right? We didn't have the mass to make it serviceable. It was cryogenic, which makes it hard. And servicing the robotics wasn't coming along fast enough. So Webb was not designed to be serviceable. So what happened was every instrument was really complex because there wasn't going to be a second or third generation. I mean, look at the micro shutters, cryogenic 200 micron micro shutters that open and close, invented just for Webb. Whereas, if you look at Hubble, we started our first generation spectrograph was just a point source, faint object spectrograph, high resolution spectrograph. You can only look at a point source. STIS came along with a slit and the imaging spectroscopy. That was second generation. So Webb had to put a lot of money into instrument technology. And that was money we couldn't use to do the rest of the thing. Like we couldn't really invest in spacecraft. We had to push it off. And that hurt us. Whereas if you could rely on servicing and you say, let's keep it really simple, keep the coronagraph to be only a little bit more complex than CGI, the one on Roman, you almost use that as a prototype as your starting point. And then maybe cost cap and one or two more instruments so that your instruments are really constrained, but you really put the money into the telescope. I think you can get up there faster. And that's the argument I was making to people before I left is there is a strategy to get up there fast. This is what, the administrator wants.
Yeah, it's going to be music to his ears, right?
Yeah.
And if he gets to fly, if he gets to be in the spacecraft that goes out there. Yeah, out to L2 to fix this thing, I think he would really appreciate that.
He probably would, although I have to tell you, I'm such a believer in robotics and autonomy. It's like, I don't even know why we're sending humans. Just send the robots kind of thing. But yeah, he probably would love that though.
Yeah. Well, I mean, he was the one who pitched the idea he pitched to NASA for reboosting Hubble and doing an on-orbit repair and doing that with a SpaceX Crew Dragon. So, this is the thing that he's thought a lot about. And so, I think this will be right in, up his alley. So one architecture that I'm quite obsessed with is just on-orbit assembly. I've been looking at a bunch of ideas for just people building space telescopes out of parts that you send up in multiple flights. I mean, that's how the International Space Station was built. Do you think those ideas have matured to the point that that's a viable alternative? Because then you just launch a big mirror and then you launch the bus, and the bus has little robot arms on it and it adds bits and pieces to it as it goes.
Yeah. I mean, I've been thinking about this question for a long time. I even did a paper in 2013. I don't know if you've seen it, called Modular Assembled Space Telescope, which was a 20-meter. How would you assemble a 20-meter telescope? And the idea is you'd send up a bunch of panels that look a lot like Webb center section. Webb center section has 12 mirrors on it. Take the wings off. And you just send up a bunch of those, and then they latch to each other and you build up a telescope. And then there was that whole study that happened about 5 years ago looking at assembly. I mean, I personally think assembly, after an 8-meter class, 7-8-meter class telescope, anything bigger is going to be assembled.
Yeah, there's no way to do it.
There's no other way to do
assembling.
It. Yeah. But what better way to transition to, and you're going to want it at L2. I mean, L2 is just the natural place to put all these things for a lot of good reasons. I mean, you could potentially have these highly elliptical orbits, but like if you need ultra stability or cryogenic, you're probably going to be at L2. And so I think it's going to happen, but I think making HWO serviceable and maybe origin service. Like, the next generation is serviceable at L2 with robotics. And then you learn how to do robotics at those long distances. And then beyond that are the assembled telescopes. And we laid this out. There was a roadmap. I actually co-chaired a roadmap in 2005. It was called the Advanced Capability and Observatory Roadmap. This was NASA did a bunch of these roadmaps, and one of them was on this topic. And this is exactly what the best people at NASA laid out in 2005 was like, service at L2, and you do assembly. And I still think it's the right strategy. I really do. And I think we'll get there. It's just everything takes longer than you thought.
But and if I was going to try to approach it from a risk perspective, I would take something that's very, high technological readiness level, but then assemble it and focus on specifically upgrading it and adding new bits and pieces over time. Don't try to also make the most complicated telescope ever built until you've kind of mastered that. So do them hand in hand, right? And then try to continue once you've built all that experience and knowledge up.
Yeah. I mean, yes. One thing is that that big barrel that's now protecting us for micrometeoroids and a thermal shield at the same time, you got to think about that. So if you're assembling a telescope now, like, what is your barrel? Is it going to deploy, or is it going to be assembled itself? And how do you assemble something that's 15 meters long? And, so it's not just, the primary mirror, but it's also that barrel and the secondary mirror. And, when you start looking at all that, anything you do it's not going to be cheap. There's this, if you're going to build a big telescope in space, even if it's not high performing, it's not going to be cheap. And so I don't think you're going to justify doing that unless you're doing something really important scientifically. You need a big community of people to be supportive.
I mean, is there any, when you think about these constraints, is there anything for kind of big and dirty versus smaller and like really well refined? Like if you went for like, we can't make it accurate, but we can make it 20 meters by just assembling, hexagon after hexagon after hexagon and lining them up. Like, is there sort of any room for that, or is it you've just got to go with like really fine tune the smaller one?
So the one idea that I pitched, which is to reduce your field of view and to use spherical mirrors instead of, one of the challenges of like Webb is every mirror, there's 3 different prescriptions that repeat themselves, but they're off-axis A-spheres, which are pretty hard to make. You need a computer-generated hologram. You got to polish it just right. Spheres are actually really easy to make. You just have a mandrel that you polish with, and you just till it's the shape of the mandrel kind of thing. So you could imagine building, and there are on the ground, there are these very low-cost ground telescopes that use spherical primary mirror segments. The SALT telescopes out, in South Africa, for example. Hobby Eberly is another one. It was dirt cheap, right? So that's one thing you could do, is you could use a spherical primary mirror, just have them all replicated, really cheap. And you get a much lower field of view. If you want a large field of view, you need really huge secondary, it gets complicated. But you could potentially sacrifice field of view, which, if all you're trying to do is the exoplanet problem, that might be a possibility. And so, there might be some way to simplify, look, like ELT, right? ELT is 39-meter mirror. What they did that was so brilliant is they figured out how to sort of automate the making of the mirrors, right? In terms of, they're using a lot of automation in the metrology and the polishing, but they're still off-axis A-spheres, everyone with unique prescriptions. It's still not cheap and easy and all that. But you can imagine like literally letting robots just stamp out mirrors, and you have all these mirrors and stamp out a structure, But if you want to be ultra stable, that gets complicated. I mean, that's really the problem. Is the really interesting problem for me after HWO would be now maybe it will either be the far infrared telescope Origins, or it'll be the next generation HWO, which will probably want to be ultra stable again. So I'm not exactly sure where that's going. I think maybe the answer is just a really big, mid to far infrared telescope Origins, but even bigger than Origins. Maybe that's what you do.
Mm-hmm. Yeah, I just wonder if like just raw strength gets you what you need, or it, because the bigger the telescope, it gets you your resolution, it gets you the faintness. And those are the things that you want in pretty much any observation you're ever going to make. And as you said, that thing that you're looking for is how close can you pick off that planet compared to its star. Infrared makes that job easier, but
and of course you've just set up my career choice, which is, I've been thinking about this problem for 30 years. I mean, I'm really, just focused on, like, how do we advance, telescopes and, our ability. And I think the real thing is we've got to get to interferometry. To this day, we've started numerous interferometers, Deep Space 3, SIM. You can go back, formation flying with a boom. They want to do far infrared. I was part of this, 1 kilometer baseline far infrared that was tethers.
Yeah, the terrestrial planet finder.
Yeah, terrestrial planet.
We're just going to cry now if we just keep having this conversation. So,
so the LIFE mission is sort of the evolution of TPFI and Darwin, but it's mid-infrared. But it is also looking at Earth-like planets, but in the mid-infrared, much in the way that, if you think of Webb, when it does exoplanet transits, it does it in the near infrared with NIRISS, and it does, or for near spec, and it does it in the mid infrared with MIRI. So this is, the mid infrared, which has all these unique molecular lines and complementary molecular lines to what HWO does. But by going, we've got to get to interferometry, and it kind of makes sense to me to start at a longer wavelength, which is easier. The shorter the wavelength, the more precise the interferometry.
Right, but also that once you're in infrared, then the brightness of the star compared to the brightness of the planet is more forgiving.
Way more forgiving by 4 to 5 orders of magnitude.
4 to 5 orders of magnitude, 10,000 to 1 or whatever versus 10 billion to 1, right? Like,
because you're looking at thermal emission of the planet as opposed to the reflected starlight, and it's just when you go through the math, it turns out it's an easier problem from the point of view of contrast, but then you have to figure out, how am I doing the formation flying? Am I using formation flying? Am I using a boom? You need it kind of scales the baseline, how far these things have to separate. If you take HWO, let's say an 8 meter HWO in the visible, now if you go to the mid infrared, it might be a factor of 20 longer wavelengths. You need a factor of 20 bigger baseline. So you might need 150 meter baseline interferometer. And that's starting to get to the point where you need formation flying. And, the LIFE idea is to spin these things. And maybe there's 4 of them, and they're interfering the light at a central interferometer. And so that's not a trivial problem. The formation flying is the hard part. But it doesn't need, the SIM needed picometer level controls, right? This is, nanometer, micron, and, nowadays with active controls, it should all be doable. You have to do it cryogenically. So, the mid-infrared demands that you're 50 Kelvin, just like Webb was. That's why one of the reasons Webb, a lot of people don't appreciate this, but like we probably could have relaxed the sun shield temperature and even the mirror temperature, if not for the mid-infrared requirement. So it really pushes you there.
And so we just very quickly shifted gears there.
Yeah.
And I'm not sure we brought everybody up to speed on what just happened there. So if you're like, wait, what were we talking about now? So you retired from NASA and you were designing HWO, doing the work on that. Yeah. And then you have unretired and now you're joining, who are you joining?
So May 1st, I joined ETH Zurich.
Right. Okay.
Yeah. In Switzerland.
And they're working on their version of the Habitable Worlds Observatory, which is the LIFE mission. And the big difference on this as well, HWO is going to be this single telescope. The plan for LIFE is it's going to be a formation flying, or perhaps a rigid, collection of telescopes that are going to be an interferometer and use that infrared as we mentioned. But there's another technology that the interferometry gives them, which is the nulling, which removes the need for a coronagraph in the same way. So can you explain that sort of that architecture to people?
Yeah. So the very simple way to think about it is imagine you have, these 2 collecting mirrors, light's coming from a star. If I take the light from each of these collecting mirrors and I send them to what we call an interferometer, I do need to keep them stable to a fraction of a wavelength of light, which requires some active controls. And if I modulate one of them by half a wavelength of light, that, and it's starlight coming in, that basically cancels the starlight. It is sort of similar to using deformable mirrors, to conjugate and to dig a dark hole. Instead of doing it that way, what you're doing is you're sort of canceling things with two mirrors. And then you get a better dark hole, if you will, using four mirrors. And there's some ideas that have, been looked at in the past that they're building on for doing this optimally, to like dig a deep enough dark hole. But it's basically the concept of interfering light together and canceling the starlight out. The planet, though, is slightly off axis. And if I rotate these mirrors around that star, if you will, when they rotate and they're lined up with the planet, all of a sudden you get a bump in the signal because the starlight cancels, but the planet doesn't. And so that's kind of the trick is to, that's one way to do this problem anyway, is to rotate. And eventually when you come across the planet, you get that bump. The starlight is constantly getting canceled because these two things are, kind of, you almost think of like waves in the ocean, like if two waves hit each other with one, peaking at the right point, they kind of cancel each other. You kind of get nothing. And that's what you're trying to do here at some level. Yeah.
And so, but then you've also got the benefit of, because these things are separated, you've built your interferometer that's giving you a bigger baseline, better resolution.
Yeah. I mean, it'll turn out to have an equivalent resolution in some level to Habitable Worlds Observatory, because Habitable Worlds Observatory works at a much shorter wavelength. So you're trying to maintain that resolution, if you will, to get as close. And you can go far, you can separate these mirrors more and get even better resolution. That's possible. It's all a question of how you want to design it. And I haven't started yet. So I have a lot of questions myself, and then that's one of the reasons I'm going there is like, what does this path look like? And what does it imply for the Habitable Worlds? And maybe what we need to be doing is like system engineering the two of them to be complementary in a way that makes sense, because they're both hard problems, but they're both really important problems that I believe both problems will ultimately happen. So I think kind of getting the right balance between the two kind of makes sense. And one of the really key things for Habitable World Observatory is that the near ultraviolet is a pretty hard wavelength band and is mainly used to find ozone. And ozone, you can also find at 10 microns, which is in the sweet spot of life. And so that's like a good example of, if we believe life is feasible, the life mission is feasible, then maybe it makes sense to have worlds put a little less emphasis on that and make sure life does a really good job with that. But these, I have a lot of questions about, what it's going to mean. And they're doing it through private funding. So, there's been this big push towards private funding. Schmidt Foundation announced that they're funding a whole bunch of private science. Personally, I'm super excited about this whole idea of private science. So like the timing was great for me in my career, because now I can go, at the beginning of the wave of private science, get involved in something that's being funded privately. But I'm also realistic enough to know that private funding might only really do technology like doing a full flagship with private funding. I mean, we'll see, maybe it's possible, but that is a challenging thing. But, a lot of times what you need initially are technology demonstrations, and maybe they build on themselves. So, that's kind of part of the excitement. And for me, it's like thinking about new ways to do this, but also bringing in the experience to say, like, let's not go crazy here. These things are harder than people think. And, let's put a plan together that doesn't rely on, unobtainium, if you will.
Yeah. I mean, it feels like, as you're sort of in this in-between stage, there's a lot of wonderful ideas that are being demonstrated and turned into actual hardware. I interviewed the people behind the Chara array, which is the world's largest optical interferometer, and just the engineering involved to make that go is absolutely fascinating. There are ideas to put like really tiny interferometer on the surface of the moon, have one of the landers land and have a little rover that goes off with really just like a tiny, like a 30 millimeter refractor on board, and then try to build an interferometer where you could be 100 meters apart and maybe you're getting images of the surface of Betelgeuse, right? That there are these ideas of people, building spherical telescopes that work in an array, and you're not trying to build an interferometer, but you have the room to just keep adding more and more of these telescopes. They can point at different targets. So there's like a lot of really interesting ideas that people are doing. The dragonfly, is it the dragonfly telescope? But people are taking like, commercial lenses, stacking them together to get larger apertures. And it feels like the ideas are out there somewhere in this combination of them. Be great to like take a world tour and
it's hard, isn't it? Because these ideas always sound great. And, then you say to yourself, well, why, it's such a great idea. Why haven't we done it?
yeah.
You know, so two thoughts. One is I've tried to really let science drive things. Let the big science questions be the driver, find the early universe, search for life, and then say, what's the best way to do that? Because a lot of times there's this great technology, but it's like when you really get into it, you'll find it's not going to do the science, very interesting science. There's some little gotcha. It's the throughput is so low. I was talking to somebody about some brilliant idea. I don't want to say what it was. And it's like, it sounded like the greatest thing ever. And then I found out it only works with like 5 stars in the sky. You need the 5 brightest stars. There's always, these problems are so hard. There's always some hidden gotcha. And it's really hard to figure out the gotcha without spending a decent amount of time. The other thought for you though, is like, these ideas are such good ideas. Somebody probably should have tried it at a smaller scale first that is doable. When I see something that's been proven at the small scale, that's why I'm a big believer in test beds. If I've got a test bed that's working, maybe it's scaled, but at least I know all the physics hangs together. And then I apply it to a science problem with all of the parameters I need, signal and noise, stray light, pointing, all of that. Then I get excited. And I find that, 98% of all these good ideas that I've heard about, they have some sort of flaw. And there probably is 2% out there that are like these new ways of doing things that are really the way to do that we should be doing. And you don't want to squelch those, but at the same time, like, I think the hype factor has been, is often, it just outweighs everything. And I've seen articles in Nature on things, and I know there's a flaw in it,
Right. Yeah. Like rotating Mercury telescopes. You're like, get back to me when you can point anywhere apart from directly overhead. Yeah. Or, I totally know what you're saying.
And sometimes it's the stupidest things that are the hard problem. It's the stray light, right? Like stray light is like one of the hardest problems in telescopes. And most of the people who go around talking about, well, why aren't you doing a telescope like this or that? They don't even know what stray light is. They have no idea. They don't understand that stray light has different components, that there's scattered light, there's specular light. You have to worry about every one of these. There's multiple paths. There's thermal emission, like stray light alone could, be a driver. And it may, by the way, getting back to our earlier conversation about incoherent light, it could be that stray light is one of the key considerations in that, like even just limiting us on 10 to the 10th. I gave a talk recently for the team about optical verification and, how difficult it is. And I said, one of the hardest things is straight light. I mean, Euclid had problems with this. Webb we found things on Webb. One of the very few surprises we had besides the micrometeoroid was some stray light paths we missed. So like, nobody ever talks about, oh, look at that telescope. It has great stray light control, but that's what it takes. That's what it takes.
Yeah. Yeah. I know. And I mean, I've experienced that in my own telescope that if you don't shield the tube well enough, then you got a bunch of light coming in. Where's this coming from? So yeah.
And your field of view, like if there's stars in your field of view, right, that can scatter. There are stars that can specularly reflect. There's when you're trying to get to the edge of the universe, the zodiacal light of the universe scatters. And then if you have a sun shield, you have, one of the hardest things about sun shield on Webb that nobody appreciated was how its shape had to be so tightly controlled so that we didn't have a stray light problem. So that's why that very unique curvature and, how smooth it was and what they call it the BRDF, the bireflective, all these details, we had to put requirements on that design. So people say, oh, it costs so much money. They have no idea what it took.
Right. Like starlight bouncing off the surface and making its way up into the telescope. Yeah. You've got to bend that all away. Yeah. That's amazing.
And it could be that as this is one of the challenges is like you look at a different part of the sky, you get different amounts. So here you are trying to calibrate it out, but it changes. I mean, those kind of details kill you. And, you got STIS, my first, Hubble instrument, Space Telescope Imaging Spectrograph. I think maybe the hardest part of it was how we dealt with stray light control, because STIS, and this is literally the workhorse instrument of Hubble, I think even today, UV spectrograph. The first exoplanet atmosphere, David Sharp, I was just talking to him last week about this, was found with STIS, right? So this is a key instrument in the history of, space telescopes. And when we were building it, there's 21 different optical modes. There's low, medium, and high spectral resolution with a far UV, a near UV band, and a vis band. Light could be going all over the place, hitting gratings. So we built this baffle system. We called it the Baffle Star Galactica. It was one of the most complex, every light path had a different cylinder, and it was like, oh my God, we had to align it. And nobody ever, when people are like, well, why did this thing cost so much? Right? They had no idea what it took to build STIS, like all the stray light control of having a spectrometer that complex,
Yeah.
And if you don't do it, will it work? It'll work, but you won't be able to do the science that we're doing.
Yeah. Well, the question I always ask my guests, Lee, what are you obsessed with right now?
Well, right now I'm obsessed with the fact that I'm retired and I'm moving to Switzerland, and I got to find a place to live. We're going out there next week. And music, I don't know if you know, I'm a musician. I'm playing a lot of jazz, which is great, training my brain a little. But in terms of, I'm probably obsessed right now with the life mission. I've been reading papers and thinking about interferometry and really how to do formation. I think the formation flying problem, to me, in interferometers is such an important one. If we want to go beyond these 6 to 7 to 8 meter telescopes, we need a simple way to do formation flying that doesn't get too complex. And I've been thinking a lot about that, like, the different ways to do that. And I think if we could come up with a strategy there, if it could be done really cost effectively, it might enable interferometry, not just for the life mission, but for other things as well.
And
so,
I mean, the only example that's even kind of trying to crack this is the LISA mission. And I mean, it's just taking so long. Right? 2035.
I mean, LISA, they're trying to do something very specific, which is measure gravitational waves using like really, practically femtometer level stuff. There is a couple CubeSat missions. There's one out of Michigan in development that are very simple formation, things, but they don't have all degrees of freedom. Like at the end of the day, if you really think about it, I have 2 collecting mirrors and I want to maintain phase. Like what I really need is 6 degrees of freedom. Like things are described X, Y, Z and 3 different angles, right? Like delta. So it's like, how do I know my phase in 6 degrees of freedom? It's really in both absolute and instability.
Right. In that if you're going to try and look at something to the right, then the light is going to arrive at one detector before it arrives at the other one. And then you're going to try and look to the left. And now you have the opposite problem.
Yeah. I mean,
how do you
use the starlight itself? And then there's this thing called a delay line. So the white light of the star comes into these 2 mirrors. And when it comes together, if you modulate a delay line, you'll get a peak. The 2 white lights, when they interfere with each other, gives you a peak. So you can get them phased using what's called a delay line. You have to be within the dynamic range of that delay line. So your formation flying metrology has to get you within that dynamic range. And then you have to maintain all these degrees of freedom. Right.
But the Char array, they solve this with carts, right? They have little carts underneath the telescopes that wheel back and forth that change the length of the legs of the interferometer depending on whether the target, and they'll move dynamically as the target is moving through the field of view, and you're to maintain that down to the right wavelength. So, it's a what is the space version of that?
Yeah, so if we were to use booms, if you were going to do like the Spirit mission and then the Spice mission out of Goddard, Far Infrared was going to be on booms. And if you have booms, it's a lot easier to know where you are and get within the dynamic range of the delay lines. But booms can only be so big. And the more general problem is formation. If I can do formation flying, I can do 100 meter, 200 meter. It's a general, so that, I think that's the trade, actually. That's the life. When I go work on life, I think I will be talking about those kind of trades. And they've made a lot of progress. I'm coming up to speed on it. So that's why when you say, what am I obsessed with? I'm like reading, I read one paper and it says, well, we went to this type of interferometer, double Bracewell. So I think I gotta go read a paper on that. So I've been trying to like read through the history of how they got there. And
well, we'll keep us posted. It has been fascinating to talk with you. And, I look forward to the next phase in your career and getting us ever closer to that first image of an Earth-sized world orbiting around a sun-like star.
Yeah. Yeah. Thank you.
Well, I hope you enjoyed this conversation with Dr. Lee Feinberg. Now, we talked about James Webb, we talked about habitable worlds, we talked about life, but there was one other concept that we also talked about, which is quantum telescopes, that there could be a way to make interferometry work at scale using quantum technology. And this is something that Lee and I talked about a couple of years ago and sort of rattled around. And he's been continuing to think about it, seeing prototypes, reading science papers, and gives me more of an update on where we're at with this technology. It was even considered for Habitable Worlds Observatory. So we've got a longer version of this interview over on Patreon, which of course we think is the best place to watch our content. It's ad-free over there, and you don't have to subscribe. You don't have to donate. You can just watch it completely for free, but without any ads. So I'm going to put a link down in the show notes. Click on that, go watch that, and you can watch the rest of the interview, including the information on quantum telescopes. Now I'm going to give you some final thoughts, but first, I'd like to thank our patrons. Thanks to Abe Kingston, Andrea Pedretti, Bear Lake Roofing, Brian Bodie, Caradwin, Chuck Hawkins, Commander Bailout, Cooper Anelli, Dark Finger, David Gilton, David Matz, Evan Pro, Greg Feely, James Clark, Jeremy Madden, Jim Burke, Jordan Young, Josh Schultz, Marcel Smits, Michael Purcell, Nordspace, OneStepForAnimals.org, Porlbuck, Rankaidu, Richard Williams, Sean Sargent, Stephen Father Munley, Team 49, Telescopes Canada, Wolfgang Klotz, and Zelda Board Galactic Defender, who support us at the Master of the Universe level. And all our patrons, all your support means the universe to us. Well, what can I say? That was so much fun. I really enjoy talking to Lee. He's so generous with his time, and yet is this legendary telescope designer and is sort of right at the very cutting edge of the ideas that are out there. And his fingerprints are all over James Webb, metaphorically, not literally. And he's been able to contribute to Habitable Worlds Observatory, and now is going to be being the architect over at Life. And so, what a legendary career as well. Man, when are we going to find an Earth-sized world orbiting around a sun-like star? This is the dream, and it just shows you how difficult this technology is going to be for us to pull off. And yet this is the thing that science fiction has filled our minds with as we imagine all of the shows that we like, Star Wars, Star Trek, Stargate. They are all settling down on Earth-sized worlds orbiting around sun-like stars and meeting exotic biospheres and aliens. And this is that step, to help us, figure out whether or not we are truly alone in the universe. So I hope you enjoyed this one. Man, it was great to be able to talk to him. And I'm sure we'll be talking again in the future once we're further down the technology pipeline, moving towards that launch date of all of these technologies. All right. We'll see you next time.